Welcome to Pomodoro Joe for Saturday, May 13th, 2023. Today we're looking at LeetCode problem 2466, count ways to build good strings. This is a medium problem. Alright, so given the integers 0, 1, low, and high, we can construct a string by starting with an empty string, and then at each step perform either of the following. Append the character 0, 0 number of times, or append the character 1, 1 number of times. Now note this 0 and 1, these are integers, so these just represent how many times you can place a 0 and how many times you can place a 1. These aren't zeros and ones themselves. This can be performed any number of times. A good string is a string constructed by the above process, having a length between low and high, inclusive. Return the number of different good strings that can be constructed satisfying these properties. Since the answer can be large, return it modulo 10 to the 9th plus 7. And then let's see, there's an example here. Low, high, both 3, and 0 and 1 are both 1. Oh, right, and the output is 8 because it looks like we can do a 0, and then a 1, and then another 1. Or we can do a 0, and a 0, and a 1, and so on and so forth. All right. So in this one here, it looks like it's just a binary, but this one we can only add ones in pairs. So that's going to change things up a little bit. All right, so we'll put 25 minutes on the Pomodoro timer and we will get started. So the first key insight on this one is to note they're not asking us to return a list or a set of the permutations. So we don't actually need to construct all of these strings. We just need to count them. So that's going to save us a ton of time and memory. All right. And all of these inputs are just integers. So this makes it really good for a recursive solution and caching. So let's start with a recursive solution. So we'll start with some result, set it to 0, and then we will return the result at the end. Now it does say we need to return the result modulo 10 to the 9th plus 7. So let's do that. Modulo power 10 to the 9th plus 7. All right, since this is going to be a recursive solution, the first thing we need to do is create our base case. So what is our base case? I guess our base case is when we are outside of our bounds, the low and the high. So we could start by adjusting these bounds up and down as we grow our string, but I think I'll make this easier on ourselves, and we'll actually do an internal recursive solution where we'll keep track of the length of our current string. That's going to make things a lot easier. So let's do that. Okay, so now we have an internal recursive solution, count good strings recurse, that just takes the length of our current string. And here we'll do these result and return the result mod 10 to the 9th plus 7. So this makes our base case so much easier. What's our base case here? Well, that's when our length is greater than our high. So that means we've exceeded our high threshold. So if length is greater than high, we return 0. We can't make any strings that are good that are outside the bounds of high. Okay, so then what's next? Well, we have two options. We can take 0 number of zeros and add it to our string, or we can take 1 number of ones and add that to our string. Those are our two options. So I'll just write that out. So I have option 1. Well, we'll take zeros. So that's going to increase our string from length to length plus 0. Okay, so in this case, we're taking the current string, which is of length, and we're adding 0 number of zeros to the end. So that increases our length to this new length. So this is going to be our recursive length that we're going to pass back into our good string recurse count. So I guess before we actually call this option, so this option will be doing something like this. We'll be saying we're going to add some zeros. This will be the new length of our string, and we'll pass it down. But the first thing we need to do before we add these zeros, let's check to see if this string of length actually falls within our window. So if it does, then we can count it and we get points, or we can add that to our result. Okay, so our result here, because we're checking to see if we're within this window between low and high, it'll equal 1 if our length is greater than or equal to low but we already know it's less than high because we made it past this check, or less than or equal to high. Otherwise, it's going to be 0. So this is just saying our result gets increased by 1 if our length is between our low and our high. And we know that it's less than or equal to high because we made it past this check, and we know it's greater than or equal to low because we're checking right here. If it's below low, then we're just going to add 0. This word doesn't count. And we don't actually need to create our result up here then, because we're creating it fresh down here. All right, so now our option 1 is still going to be this recursive call on length plus 0, and our option 2 will be a recursive call on our length plus 1. So essentially we're just going through and saying we're going to add our 1s to this current length string to get a new length string. And then at the end, our result, well, that's going to be option 1 plus option 2 plus our current result. So in this case, instead of calling this option 1 and option 2, let's just save ourselves a little bit of memory, and we'll just add these directly to our result. And at the very end, we will return the result modulo our mod value here. And this should do it. Now the last thing we have to do is we have to actually kick off the entire thing by calling our recursive call. So outside, we will return our recursive call. Whoops. Starting at length 0. All right, so this looks pretty good. So we're going to start off with some recursive function that just takes the current length of our current string. If that length is greater than our high, then we return 0. We can't add anything to this to make it fall within our window, so we return 0. Otherwise, we can check to see if we have something that's greater than our low, greater than or equal to our low threshold. And if we do, then we know it lies somewhere between high and low, so we can add 1 to our result. Otherwise, we just add 0. In fact, we just initialize our result, in this case, to 1 or 0, based on whether or not we're within this window. Then we can go down and we can recurse. So we add our 0 number of zeros to the length in one option. The other option is we add the 1's number of 1's to our length, and we recurse, adding those values to our result. At the very end, we return our mod value. Oh wait, I need to change this to 1. Try that again. And we pass. Let's see how we do when we submit. Now, most likely this recursive function will not be fast enough. But if you've watched my other videos, you know that we can just add caching to this function to make it a lot faster. So we'll try that in a minute if this doesn't pass. And it doesn't. We only beat 14 out of 36 test cases. So let's add this test case to our test cases, and we will add caching to our function. So if you're not familiar with caching, so there's a library in Python called functools. So from functools, we will import cache. Now cache is just a function decorator, so we add it before our function with the @ and then cache. And what this will do is for any input, it will run the function one time, then cache out that result. Next time this same function gets called with the same input, instead of running the function again, it will just return the cached result. So it saves us a ton of processing. All right, let's see if this works. Still works, and it passes this one test case where we ran out of time before. Let's see if it passes all the test cases. And we pass. And we do okay for a recursive solution, not too bad. 39% for runtime, 37% for memory. Yeah, that's not bad at all. So there are things that we can do to this to speed it up. So we can jump back here. If we wanted to, we could go through and make some changes. I think, let's see, what's the best thing that we can do here? Well, one is we're making the same mod call multiple times. That's going to slow us down. So let's jump up here, and we'll just create one mod value. Create that there, and then instead of doing this pow and +7 multiple times, we'll just do mod val. That should save us a little bit. Let's try that. And it does. So we're at 58% for runtime and 37% for memory. So yeah, that is the simple recursive solution to this problem. Now, if you want to go faster, you'll probably have to do an iterative solution. And for that, well, let's just start over and try this again. So if you watched yesterday's video, I'll try to leave a link in the description because I can't remember the number it was, but you can imagine this, instead of doing this recursive solution, you can imagine keeping track of all of the values or the results for different lengths of strings. And if we did that, then we can do this iteratively. I'm going to keep our mod value here because that might come in handy, but we'll create this, let's see, I'll get rid of this too. So we'll create this iterative solution. So now in the iterative solution, instead of keeping track of just one result, I'm going to be keeping track of all the results for different lengths of string. So you can imagine if I had some length of string. So previously in our recursive solution, we were just looking at lengths of strings. If I have some length of string and I want to add 0 number of zeros to it, it's going to increase that length by 0 number of characters. If I look backwards and say, well, how many strings did I create for the current length minus this number of zeros, then I know how many more strings I can make once I add these zeros. Let me see if I can explain it as we go. So we'll start with some results, but instead of having a single value, we're going to keep an array. Now this is going to be a little bit tricky and there's going to be a little bit of leap of faith here, but we're going to start our results as 0 times our high value. So let me put a note here actually. So the index is going to equal the string length. So index 0 will be a string length 0. And so essentially we can have one of those. That's our empty string. Plus, I'm adding 0 times high because we need at least that many. We need to go up to length high. That'll be at index high plus 1. Now we're going to go through every possible length of string. So for I in range, we're going to start at string 1 because we already know our 0 is just the empty string. And we're going to go to high, but we have to add 1 here because this range is non-inclusive. So it's not going to include high if we just went to high. So we have to go to high plus 1. All right. Now at this point, we basically do the same thing we did in our recursive function. We have our result, but in this case, instead of just doing a single result, we're going to say our result for this I. Well, that's going to equal, let's see, we can actually add everything from the results if we look backwards. Yes. From this I minus our 0. So we're going to look back to all the strings that we could have created before we add any zeros to this string. Then we add our zeros. So we're going through, and for every length of string at index I here, we need to look back to see, well, how many strings did we create before we added this number of zeros? And the answer to that will be at the results at I minus 0. Now we can take that result and add it to our current result. Okay, and then we can do the same with ones. So we can basically grab this and say, how many strings did we have previous to this current length string? If we look back at how many strings did we have before we added this number of ones, now we can add that to our results at this index as well. Now I do want to make a slight variation here because what if 0 or 1 is greater than our I? Then we're going to be in negative indices here. So we should check. That's only if 0 is greater than or equal to I. Oh, sorry, I should say if I is greater than or equal to 0, because we're looking at our index. We're moving our index or our length up. All right, otherwise we just add 0. Same thing here. If I is greater than or equal to our 1, else 0. Now I'll show you in a second that this isn't strictly necessary in Python, but in other languages you will probably need to do this. So now we're increasing our result here. At the very end, well, how many strings do we end up having? Well, that's just the sum of all these lengths of strings that exist in our results, but only between our low and our high indices. So here we'll return the sum of our results. But we have to go between low and high. Again, this is non-inclusive, so we say high plus 1. And then we have to mod this whole thing by our mod value. Okay, so this should do it. We're going through every single possible length of string. We're going to check back to see how many lengths of string were we able to create, or how many strings were we able to create before we added this number of zeros. Then we can take that and add it to our current result, because we were able to add that many zeros to create essentially the same number of strings here. Plus, how many strings were we able to create before we added a bunch of ones? Let's go back and take a look. Then we add our bunch of ones and we add that to our result at this length. Okay, let's see if this works. And that works. Let's see how it does. It does okay. It does actually worse than our recursive solution. We only beat 23% for runtime and 9% for memory. But there's some things that we can do in Python that you can't do in other languages. All right, so a couple things that we can do here. The first and easiest one is probably this right here. So one thing we're doing is we're checking to see if we have an index that's greater than our 0 index. Now, in almost every other language, this will be essential. You can't look at negative indices. You'll be out of bounds and you will crash. But in Python, you're actually allowed to look at negative indices. And in our case, because we've filled this with zeros, if we look back and we go into a negative index, we're just going to return a 0 here, which is what our else case will do anyway. So we can actually save ourselves this if statement right here. Now that's just a quirk of Python, or a feature of Python. Not every language will let you do this. And that still works, which actually simplifies this quite a bit, because now we don't need two separate result adds here. We can just do one by doing this. So now we can just add our zeros and our ones at the same time to our results. That still works too. And now the final step in this, well, let's run this and see how it does. 29%, so that gets us up from 23%. It's not that much of an improvement, but the final piece of this is oftentimes these are going to be very large numbers, and we are only doing our mod at the very end here, which means that we're going to be adding very, very, very large numbers, which can actually be very computationally intensive. So if we just wrap this whole thing, we'll do our addition of our zeros and our ones, then let's do our mod and store that in our results, which means that we'll be storing much smaller values in our results, and when we do these adds, they'll be adding smaller values. That should help us quite a bit. All right, one more submit here. We're at 97% for runtime and 65% for memory, 66% for memory. So this is a huge performance gain just by storing the modded value instead of storing the value directly. Now we can still make a couple little changes here to clean it up. We can get rid of that. We can clean up some of this white space. We'll still keep our mod values. Everything else looks pretty good. We could change some of these variable names to make them shorter. It makes it a little bit easier to parse. But I think this is going to be probably best that I'm going to do today. 97%, not really any change there. All right. Oh, but we are at 70% for memory, so it's a gain. Okay, that is it for me. Hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.